Hello, my name is Siddharth Mahimkar.
And I'm Daniel Vandenberg.
This is our ECE 4881 Introduction to Robot Vision project.
For our project, we worked on the vision system for our robot OHM. OHM is an autonomous robot designed to compete in the annual Intelligent Ground Vehicle competition held at Oakland University.
The challenge of this competition is to autonomously navigate a field while avoiding obstacles like construction barrels, staying between white lines, which act as lanes, and then reaching selected GPS waypoints as fast as possible. To achieve this, OHM uses a LiDAR to detect the obstacles, a Logitech webcam, which we will go into more detail how the vision system actually works, and a differential GPS to aid in navigating between waypoints.
Here is some drone footage from the 2017 IGVC. You can see the obstacle barrels and the white boundary lines. Unfortunately, this year it rained heavily before the competition, so the lines were faded and the grass was extremely reflective. It was difficult for many teams to track the white lines. Next year we will be looking into polarized filters for the cameras.
This is our software architecture. It is written in C++ and OpenCV using the Robot Operating System framework. Each block can be considered a separate node, which is a separate program, and data is passed between nodes, which ROS handles automatically. For this project, we will be focusing on the camera and white line detection. The white line detection program finds where the white lines are and passes their location to obstacle avoidance, which figures out how exactly to avoid, and to a global mapping program, which figures out where is this white line in relation to the field. Here you see our image processing pipeline. What we do is we take the input from the camera, do a perspective transform. From that perspective transform, you get a warped image. Then we change the color scheme to HSV. We apply thresholding to determine whether what we found is white or is it not white. From that, we have a thresholded image, which just has white or black. We find out the white pixels, then we calculate the distance to every single white pixel, and then that data is passed to either global mapping or obstacle avoidance.
As Sid just mentioned, the first part of our pipeline is getting the input from the web camera. We are just using a basic web camera and a 3D printed mount to hold it to the same mast that holds our GPS. The next part of our pipeline is the perspective transform, or image warping. This is important because it gives us a top-down view of what the angled web camera sees. This is really important because the relative distance of objects in the image is maintained during this transformation. Later on, we're going to use this warped image to find out the physical distance that the white lines are away from the robot. There is a downside to this method, however. Pixels that are farther away from the robot and along the edges of the image get warped and distorted. In order to deal with the distortion caused by transforming the perspective of our image, we are going to crop down to a special region of interest. It will be approximately 4 meters in front of the robot and 2 meters to either side. This region is large enough for our purposes in IGVC. The lanes will be seen and will be far enough forward for the robot to plan where it's going to go. By cropping to this size, we don't have to worry about those distorted pixels. At the farthest distance, the error will only be about 2 centimeters. Here's an example of the image warping being performed. In this original image, we see what the robot initially sees. In the second image, we see the top-down warped perspective. This view has also been cropped in to our region of interest.
We created a camera and calibration setup guide, which helps us easily configure camera parameters. What it entails is using a stick called OHM calibration stick, which is about 1.5 meters long. We place it in front of the robot, then we place the trifold. Knowing the sizes of the stick and the size of the trifold, we know the distances of each corner. What we do is we open Cheese, which is a camera app in Ubuntu, set its resolution, get the picture, open the picture up in GIMP, then get the pixel coordinates of each corner. Once we have pixel coordinates, we input them into a configuration file. We also give the aspect ratio of the trifold. From this given data, OpenCV does what is known as a keystone correction. We run code. Once we get the correct warped image, we save the still image of the warped image. This saved image will be used later when performing a linear algebra calculation to map the pixels to an associated x and y distance from the robot, which we will be discussing more later on.
The next steps in our pipeline are converting the color scheme of the images into HSV, and then performing thresholding on the images to isolate our white pixels. OpenCV uses the BGR color scheme, which is essentially the same thing as RGB, it's just that the order of the values are reversed. We want to convert our image to HSV so that we can threshold using the value. After we have converted the image to HSV, we can perform our thresholding. We make use of an OpenCV function called inRange to threshold our image based on the chosen HSV values, and we use a slider GUI to easily change those values. The end result of this process is an image that is only black and white.
This is how we find our white lines. The image gets warped, and then we change from the BGR color scheme, which is OpenCV's default, to HSV, which is in the top middle. Then on the right side you can see sliders in the window labeled Final. As long as the HSV values are within the range given, it will be considered white, and the rest is considered black.
Once we have performed the thresholding, the code quickly loops through the image pixel by pixel and records the coordinates for every white pixel. The code stores this data for the next and final process, calculating the distance of the white pixels. Just having the white pixels is great, but in order for the obstacle avoidance and path planning portions of OHM to make use of this data, we need to calculate the physical distance to the white pixels. This is why we performed the perspective transform earlier. Now that all of the pixels are in the same plane, we can use some linear transformations to accurately calculate the distance. On the left side of the screen, we have a visual representation showing the selection of opposite corners of a calibration panel. Our example, U's are the distance in the x direction using meters, and V is the distance in the y direction using meters. The center axis that runs along the picture is the x-axis. To the left of the line is negative, to the right is positive. On the right side of the screen, we have the equations for calculating the constants for the linear transformations. If a panel of known size is set, preferably centered, at a set distance away from the camera, we will know the physical distance to the corners of the panel and can then associate pixel coordinates to these physical distances. If you recall from earlier, in the section about calibrating the perspective transformation, Sid mentioned saving a screenshot of the warped image and using the OHM calibration stick. By using this calibration stick, we will have a reliable way to get the calibration panel centered and placed in a known distance. Now, since the image has been warped, we will still have to manually find the pixel coordinates of the corners of our calibration panel again. We did this simply by opening the image in GIMP and hovering over the corners. The code running the setup of the robot will ask for the pixel coordinates, and then automatically calculate the constants needed for the linear transformation. It then stores these values in a configuration file. Here's a demonstration to show that using this method for calculating distances works. We placed a small sheet of white paper on the floor so that OHM could see it. It is approximately 2 meters away and about 30 to 40 centimeters to the left. Here we see the results of our calculations. It is important to note that the HSV conversion and thresholding are still being performed, but we're just not showing those displays. On the left is the original image. In the center is the perspective transform with the white pixels selected, and on the right is the data about the white pixels. The first two numbers are the x and y distances, followed by the pixel coordinates. Note how the x distances are negative, indicating that the paper is to the left of the axis. This screenshot only shows the data for 23 white pixels, but it is still calculating them all. This is Ohm driving through the field. Again, you can see the lines and barrels. Our vision project was important for IGVC, but it also represents what is possible for self-driving cars. Line tracking is a very important notion in robotics because it is relatively easy to implement and gives precise navigation information. From this project and our class, we learned a lot about image processing and the basics of robotic vision. We were able to compete in the 2017 Intelligent Ground Vehicle competition, and we look forward to competing again next year. If you are interested in having a look at our code for our project, we have a GitHub repository with the program and configuration file. Here is the link, and it will also be in the description of the video. If you do take a look at the code, be aware that it requires ROS and that ROS only works on Linux systems. Thanks for watching our video.